Today we are going to look at an interesting topic of database replication. In the modern era of big data, data replication is everywhere. From bank accounts to Facebook profiles to your beloved Instagram pictures, all data that people deem important are almost for sure to be replicated, right? Across multiple machines, across multiple availability zones, across multiple data centers. Okay, why we do the replication? So replication is required to ensure data availability and durability. Okay, so in today's video, we are going to explore one of the most common replication strategies, and that is called the single leader replication. Okay, now let's look at some keynotes here. Let's deep dive into it basically. So, yeah, so we are going to look at single leader replication. Okay, so first of all, let's understand how many types of replications exist. Okay, or we can replicate the data with. Okay, so first of all, there is a synchronous replication. Okay, then there is asynchronous replication and hybrid replication. Okay, so hybrid is usually called the partial sync replication. Okay, fine. So this is a very basic diagram of how replication works. Okay, let's say we have a leader database somewhere. Okay, we have a leader database here. This is the leader database, okay, which we call the master node where all our data is stored. Okay, this is a user from any application, user from social media application, user from any video streaming application, okay, user from any banking account application, whatever application can be. Okay, the data is there where we use as a persistent storage. Okay, so user makes a write request to the database. Okay, so basically the request goes through the backend server, and then backend server triggers the database and data is stored. Okay, so we are not actually, I have not actually represented here backend server. We are directly dealing with the database. That's why I have just skipped that part. Okay, so this is the leader database where our data is stored and it can be used as a reliable data source. Fine. Now, how the data is replicated, like, so it's up to us how many copies we want to keep in one particular zone, and how would we want to replicate over the different data centers over different regions. Okay, but let's talk about only one data center for now. So we have a leader database, okay, and we have two replicas which we call the follower. Okay, the follower 1 and follower 2. Fine. So what leader does that whenever the user sends a write request means whenever user does any transaction, okay, transaction over the network, doesn't it, it is not necessarily the payment transaction. The transaction means simply user makes an API call which includes some write call. Okay, user needs to modify some data on the database. Okay, so that data lands here at leader node, or what we call the master node. The master node then forwards the request. Okay, the forwards the request to the follower, to the replica node, correct, and it waits for the acknowledgement. Okay, when the acknowledgement is sent from the follower node, so when the data is replicated correctly on the follower node, then acknowledgement is sent back to the leader node. Fine. So whatever replicas we have, right, I mean whatever number of replicas we have, the leader will send the parallel forwards to all of the replicas, and it will wait for the acknowledgement from all of those. Okay, so this is called sync replication actually. Why synchronous replication? So synchronous replication means something like this, that until, okay, so this is leader, okay, and we have follower 1, means replica 1, replica 2 and replica 3. Until we replicate data to all the replicas, we don't want to get back to the client and provide the response. Okay, but think for a while and pause the video for a minute and let me know that is it really needed to replicate data on all of the servers. Okay, no, right, I mean if you do this, then it's not going to be efficient. The client has to wait for a lot of time. Okay, let's look at with some analogies here, with some graphical representation. Okay, so let's say this is a client, okay, and I have represented here 3 times. Let me also denote it here, t equal to 0. Okay, so client is making a request at t equal to 0 unit. Okay, you can call it as second. Okay, so client is making a request to the leader node. Okay, this is a write request. Okay, we will talk about the read request. Okay, this is a write request. So client is making a write request to the leader node. Then what leader will do? Leader will try to replicate this data onto two followers, because two followers exist in our ecosystem. So at the same time here, it will propagate this data to two followers. One is here and one is here. Okay, forward the data. Fine. So at t equal to 1, the follower 2 has received that data from the leader. Okay, it will try to send acknowledgement, and here somewhere, I mean somewhere between t1 and t2, let's say this is t equal to 1.7. So at t equal to 1.7 second, the leader has received the data. Sorry, received has acknowledgement from the follower 2. Okay, but notice the pattern here. Okay, while leader is sending this data to follower 1, okay, due to some network delay or due to some poor network speed or for whatsoever reason, some delay is happening in transmitting the data to follower 1, right? And as soon as the follower 1 receives data somewhere here, let's say this is t equal to 2.4 second. Okay, so follower 1 has received the data at t equal to 2.4 second. So it will try to send an acknowledgement back to leader here somewhere. Okay, at t equal to 3. This is the acknowledgement, you can say. Okay, and as soon as the leader receives the acknowledgement, because now leader has acknowledgements from both followers here as well as here. Okay, so leader is now ready to send the response back to client. Okay, so leader will send the response here somewhere. So response is sent, let's say 3.5 second. Okay, so what is the time span here in order to send the response back to the client? So it almost took 3.5 seconds, right? 3.5 seconds. That is not good. That is too much time. Okay, it is called the super late. Okay, so we don't want this strategy to be happen, but for very critical applications where we need to follow this approach like sync replication is required, then only we do this kind of stuff. Okay, like where we don't want the efficiency in terms of, or where the network latency is accepted to a greater significant amount, then this strategy is followed. For example, in a bank account, right? So when we do the transaction, when we do the payment, right, so payment needs to be propagated, payments entry, or more specifically the historical records needs to be present on all of the servers, on all of the availability zones, on all data centers, right? So where we can follow this strategy, but there is a simple, I mean we can also improve this. This is not the correct methodology to use this approach in banking account application as well. Okay, so this is one thing to consider. Okay, now let's look at here what are the issues. Okay, what are the issues with sync replication? So one of the issue we see that it takes a lot of time to respond back to the client, because leader has to wait for the acknowledgement from all its from all of its replicas, from all of its followers, and then it will propagate the response back to client. Okay, so this is one of the major issue. Okay, the second issue is, let's say I have a leader here. Okay, I have a leader L. I have a follower F1. Okay, F2 and F3 here. Okay, now when leader sends data, when client sends write request, leader will try to propagate that, or try to replicate the data onto follower 1, 2 and 3. Okay, but somehow due to network partition, or again for whatsoever reason, the leader is not able to communicate with follower 3, or maybe due to some internal resource consumption at follower 3. Maybe the data is received at follower 3, but it is not able to send the acknowledgement back to the leader. Okay, but here leader is bounded to receive the acknowledgement from all of its followers. It is not receiving the acknowledgement from follower 3. That means it will not be able to send response back. Okay, so client will wait indefinitely here. Okay, in other words, what would happen, that the request would timeout at client's end. Okay, so let's say if timeout is of 10 seconds, so after 10 seconds the request would timeout and client may try to do the same thing again. Okay, so what is the resolution here? Resolution here is that either we remove this node if we can't find the immediate resolution from the replica list, or we manually restart this node. Okay, but while we do this, leader will not be able to serve any of the client's request, and that is good, right? So here we are I mean, if you have heard about CAP theorem, okay, consistency, availability and partition tolerance. Okay, so here it is not it is not providing the availability, because leader is not able to take any write request, or maybe leader is able to, but it is not providing the response back. So availability actually here is broken. Okay, so that is not good. Okay, now failover. Okay, what is failover with the sync replica? Failover is what? So every write request, okay, the user is sending every write request to leader, okay, and leader is then obliged to send the data to every replica, follower 1, 2 and 3, means replica 1, 2 and 3. Okay, now every node, every replica and leader is interconnected so that they can communicate and they can send data back and forth. Okay, now here we will see that what if, okay, so if replica is broken down, then we, okay, so if leader breaks down or not available, then any of the follower, okay, can become the leader and accept the write request from the client. Okay, and this is acceptable because every follower is in sync with the leader, okay, until leader was available, till the leader was available. Okay, so the failover with sync replica is not that complex because the followers are having the up-to-date copy of leader. Okay, so any follower can become a leader and they can accept the write request from the client. Okay, how the follower become the leader? Okay, so we will use a component called zookeeper. Okay, so zookeeper will be central in our ecosystem, and leader and followers are registered to there, and zookeeper keeps sending the heartbeat to each and every follower as well as leader, and if heartbeat is not received, then leader will mark that particular component as either leader or follower as down, and it will just remove an entry from the nodes list on the zookeeper. Okay, so that is how the failover would work. Okay, before we deep dive into this async replication. Okay, let's see here that how the client, uh, okay, we will go it here. Okay, so here we have seen that client will send the write request to leader. Okay, but we have not talked that why the read request is sent to followers only. You have seen this, that followers, right? Why it is not sent to leader? Okay, so if leader is accepting both write request, okay, and read request, then it would become heavy, right? I mean, for read heavy applications like Facebook, Twitter, okay, for an application like YouTube where we need to continuously stream the videos or where we need to keep posting something. Okay, so for read heavy applications, the leader would be bombarded with too many requests, and ultimately there are chances of having it broken down. Okay, so due to the consumption of the memory resources and CPU utilization, it will go down and eventually it will be crashed. Okay, so that's why we will not utilize reader to send read request, but we will use the follower, I mean any of the follower to send the read request to. Okay, because follower is also having the same copy as leader. Okay, fine. So this is why we use the followers for the read requests. Okay, now here let's see the async replication. Okay, async replication. So why async replication is required? Okay, so let's understand a small diagram here, right? Okay, so here the client sends a request to leader here somewhere. Okay, let's say at t equal to 1, here at t equal to 1. Okay, and leader immediately sends the response back to the client. Okay, because this is async replication, means leader doesn't want to wait for the follower 1 or follower two's acknowledgement. Okay, it is absolutely fine if it is replicated behind the scene without informing the client, or without waiting for the acknowledgement. Okay, what is the advantage of using the async replication? That client doesn't have to wait. I mean, the response can be sent within few milliseconds or within 1 second. Okay, and that is a great, I mean, so that we have achieved the time latency very much here. Okay, and then client can forward the request to follower 1 and 2, and then can send acknowledgement to leader eventually. Okay, at specific timeout. I mean specific seconds. Okay, now here that okay, but we also have some disadvantages for async replication. Okay, what are the disadvantages with async replication is that, let's say leader, okay, so leader has sent a request, or maybe leader has forwarded the request to replicate the data to follower 1. Okay, so this is called forward 1 and this is called forward 2 to follower 2, but somehow the follower 1 has not acknowledged back to the leader. Okay, but leader has already sent the response, okay, before sending this forward request to the follower 1. Okay, so client may assume that his data is replicated onto the backend systems or onto the database, but the data is not actually replicated on all the nodes. Yeah, I mean data is replicated here, but it's not replicated here. Okay, so this follower is called now out of sync replica. This replica is called out of sync replica. Okay, why out of sync? Because it has missed the data replication event from the leader. Okay, and going forward it will be behind, so we will manually restart this, or there are some tools and techniques. We can also write some few algorithmic scripts to restart this follower and can catch up with the leader later. Okay, so that is one of the consideration when we use the async replication. Now, how to handle the read issues? Okay, okay. Why the read issues are important? So let me draw something. So let's say, okay, I am drawing it something like here. So this is called follower 1. This is called follower 2. This is called leader. And above we have a client. Okay. So I am again putting a timestamp. Okay, different timestamps. Okay, now client has sent a request, let's say at t equal to 0 second. Okay, client has sent a request like key and value. So the key is something like fruit and value is 2. Okay, so leader will write this request to its node. Okay, then what leader will do? Leader will forward this request to follower 1, and at the same time it will also forward this request to follower 2. Okay, and it will wait for the acknowledgement somewhere here. Okay, so fine, so the fruit 2 will now be written here and fruit 2 will now be written here at follower 2. Okay, now consider the case when client or a different client, okay, wants to read the key fruit. Okay, so there is one write request. Let me change the pen. There is one write request where we have updated the database with key fruit and value 2. Okay, so this is coming from client A, let's say. Now client B makes a read request to, okay, so we have discussed, right, that read request can be sent to followers. Okay, it can't be sent to leader. It is not like we can't send to leader, but because we want to prevent the leader from from being crashed, and we want to we want the leader to be efficient for the write request. Okay, that's why we are forwarding our read request to the followers. So the client B has made a read request for reading the value of fruit. Okay, but let's say the client has made some requests somewhere here to follower 2 at t equal to 2 timestamp. T equal to 2 timestamp. This is client B. Okay, so the client B, this fruit value is written at somewhere 2.5 seconds. Okay, but client has made a request before that. Okay, so either it will see the old value of fruit or it will see the no value present. Okay, so this is called stale data. This is called stale data. Even though the client B has sent the request, after client A has written the request, okay, the client B received the stale data because it was not replicated yet to the follower 2, right? I think you got this problem. Okay, so how to get rid of this? Okay, so we are having two terminologies. One is read after write consistency. What is read after write? So we will only read the data once write happens. How to ensure that? Let's say I'm using an application of facebook.com, okay, where I am putting a like button okay, where I am putting a like button somewhere on my post, okay, like count will be increased. Okay, so I am making a write request. Okay, when I press the like button, I am literally making a write request to the Facebook server so that my like count will get increased, or that post like count will get increased, and it will give me the updated data. Okay, now what happens that if I refresh the page, okay, and my like is undone, okay, so I will assume either something went wrong in my previous like press, and I would again I would again press the like button, okay, to make it happen. Okay, but that is not the case. So what I would do that when I press the like button, I will store the timestamp in my client, means in Facebook application. Let's say like button is pressed somewhere at 2513. Okay, 13, and we will also store it in terms of milliseconds. So let's say 47, something like that. Okay, so when I refresh the page, or when I again reload the post or my home timeline, that I will send this timestamp to the server. So what server will do, that server will give me the data or give me the events which was written to the database after this timestamp. Okay, so I have leader, I have replica 1, replica 2, and replica 3. Okay, so let's say the event was written here at 2:05:13:61, here to let's say 06:14, and 2:05:13 41. Okay, so see, this 41 was happened before 47. Okay, then again this is happening lately, right, and this is also happening lately. So we can provide data what is the latest one. Okay, so we can serve the data from replica 2 and can provide the response back here. Okay, so this is how we achieve the read after write consistency. Okay, fine. Now providing monotonic reads using sticky session. Okay, how to do that? Let's say I have a leader here. Okay, I have a leader, and I have a replica R1, okay, R2, and R3. Okay, so leader, we are not considering leader because we are making the read request. So let's consider load balancer here. Okay, so load balancer can either forward request to R1, can forward request to R2, or can forward request to R3. Okay, this is the client. Okay, now if R1 has some data, let's say, R1 has some data which has version 4. Okay, and R2 has some data which has version 3, and R3 has some data which has version 4 again. Okay, so when client wants to read data back from the client, okay, yeah, so when client wants to read data back from the client, when client wants to read data back from the replica, what will happen that sometimes the client request may fall to replica 1, so it may give the data with version 4, or sometimes the client's request may go to replica 2 and it will give the data with version 3. Okay, so client may see the inconsistency in the data. Client will see the inconsistency in the data. Okay, so what we want to do, so we want to avoid this we want to avoid this random reads from going our request, or from sending our request to random replicas. Instead, what we do, we use the load balancer. We use the strategy called sticky sessions. Okay, we use the strategy called sticky sessions. Okay, why the sticky sessions are needed? So that, let's say this is client A, okay, and this is client B. So client's A's request would always go to replica 1, and client's B's request would always go to replica 2. Okay, so whatever data this replica has will always be seen by the client. The client will not see the inconsistent data, like sometimes he sees the value 2, sometimes he sees the value 3, sometimes he sees the value 10, whatever. But if client wants to see the consistent data, okay, even if it is tail data, that is okay, that is still acceptable. But to provide some sort of consistency, we will use the sticky sessions. Okay, so that is one of the that is one of the mechanism we can use to handle the stale read issues. Okay, now the next thing is how to handle the network partition. Okay, so uh, let's say I have a leader. I have follower 1, I have follower 2, and I have follower 3, right? Fine. Now I have leader, follower 1, 2, and 3. Now, I mean, for some reason, for whatsoever reason, the communication between leader and follower 1 and 2 are broken. Okay, so leader doesn't know where the follower 1 is, leader doesn't know where the follower 2, only leader knows the follower 3. Okay, so there is literally a kind of partition between okay, so this is forming a cluster here now. Okay, what we call the sub cluster. Okay, and this is another cluster. Okay, this sub cluster was formed because of the network partition. Okay, so this is sub cluster 2 and this is subcluster 1. Okay, now what will happen is that because this subcluster 2 has no leader, okay, I mean both of them are followers, so zookeeper or maybe not zookeeper but internal communication mechanism between followers will try to elect one of the follower as master node or leader. Okay, so let's say this is becoming a leader here somewhere. Okay, and this is already a leader, so we have two leaders in the system, one leader in this subcluster and one leader in this subcluster. Okay, so who will accept the write request? Let's say both of them are accepting the write request from the client, so it will again end up in a conflict when replicating data over followers, right? So this is called split brain situation. Split brain means we have formed the subcluster because of the network partition. Okay, so the system is not in the whole ecosystem, the system is not able to figure out who the leader is or who the data is replicating to. Okay, so how to get rid of this? So we will use a technique called quorum and fencing. Okay, so that itself a different topic, we will not go into detail, but that comes to the rescue here. Fine. Now, what is the best possible? So far we have seen the synchronous replication and asynchronous replication. Okay, and both of them are having advantages and disadvantages, but async replication wins if we compare it to the sync replication. Okay, if we just put aside the data durability for a moment, but if we want to achieve everything, okay, so I'm not saying almost all application, but most of the application would use the hybrid pattern or what we call the partial sync mechanism. Partial sync is what? Let's say client has sent a request here to leader. Okay, so leader here is configured. Let's say leader has 5 followers. Okay, so what sync was doing? Sync was getting acknowledgement from every followers. Okay, what async was doing? Leader was not waiting for a single acknowledgement, but here in partial sync we can configure the leader to get at least 1 or 2 acknowledgement. Okay, that is configurable. We can also configure if we have, let's say, 1000 replicas, 1000 followers, and if leader can receive 10 acknowledgements from any of the 100 followers, from any of the 100 replicas, that is fine, but some number is tunable, some number should be configurable. So if leader receives, let's say here in our case, if leader receives at least 1 acknowledgement from 5 followers, we will ensure that our data is replicated and safe. In case leader goes down, 1 copy is available on any of the follower. Okay, that is in sync with the leader. Okay, so that's what this diagram depicts. Fine. So this is called the partial sync mechanism. Okay, so we have a few in sync replicas here, not all or not any of them, right? Yeah. So so that's it for single leader application in this part 1. We will again come up with some more application topics in the upcoming video. But if you like this content, please do like and subscribe. Okay, and keep sharing to your network or friends whoever are interested in learning this topic. Okay, we will again meet for some interesting system design topics. Okay, till then, goodbye.